Fact 1. The solar system's vast, icy shell. Imagine our solar system, not ending with the distant orbit of Neptune, but enveloped in a colossal, spherical shell of icy bodies. This is the Oort Cloud, a theoretical realm so vast it marks the true outer boundary of the Sun's gravitational influence. Named after Dutch astronomer Jan Oort, this cloud is a sparse collection of trillions of comets, frozen time capsules from the formation of our solar system over 4.5 billion years ago. They drift in a slow, silent cosmic ballet, held loosely by the Sun's gravity at distances thousands of times farther than Earth. Light from the Sun can take over a year to reach its outermost edge. It's a place of profound quiet and cold, a silent sentinel guarding the frontier of our cosmic home, holding the pristine ingredients that built our worlds. Fact 2. A realm of two parts. The Oort Cloud is not a single, uniform structure but is thought to be composed of two distinct regions, a vast outer spherical cloud and a disc-shaped inner cloud, sometimes called the Hills Cloud. The outer sphere is the most famous part, extending perhaps a light year or more into space, almost a quarter of the way to our nearest stellar neighbor. This region is only weakly bound to the Sun, making its inhabitants susceptible to gravitational nudges. The inner, disc-shaped cloud is a reservoir, a source that slowly replenishes the outer cloud over billions of years. Together, these two parts form a dynamic system, a massive, ancient repository of comets whose structure tells a story of gravitational tides, stellar encounters, and the deep history of our solar system. Fact 3. The birthplace of long-period comets. The most breathtaking, once-in-a-lifetime comets often begin their journey in the Oort Cloud. These are known as long-period comets, celestial travelers with orbital periods lasting thousands, or even millions, of years. Their journey to the inner solar system is a result of a gentle gravitational disturbance. A passing star, a giant molecular cloud, or the tidal forces of the Milky Way galaxy can subtly perturb an object's orbit. This slight nudge is all it takes to send the icy body on a new, highly elliptical path, falling inward toward the Sun. As it approaches, the Sun's warmth vaporizes its ices, creating the beautiful coma and tail we observe. Each of these comets is a visitor from the deepest, coldest part of our solar system, a messenger from a realm we have never seen. Fact 4. Not formed in place. One of the most fascinating aspects of the Oort Cloud is that its trillions of icy bodies did not form in that distant, cold region of space. Instead, they are exiles. These comets are believed to have originally formed much closer to the Sun, in the same region where the giant planets, Jupiter, Saturn, Uranus, and Neptune, were born. In the chaotic early days of the solar system, the gravitational fields of these massive planets acted like giant cosmic slingshots, flinging countless smaller icy planetesimals. Many were thrown into highly elongated, distant orbits, not quite escaping the Sun's gravity. Over millions of years, these objects settled into the stable, distant orbits that now form the Oort Cloud. Fact 5. A link to interstellar space. The Oort Cloud exists in a unique transitional zone, a cosmic no-man's land between our solar system and the vast interstellar medium. At its farthest reaches, the Sun's gravitational pull is incredibly weak, barely stronger than the background pull of the Milky Way galaxy itself. This means the Oort Cloud is not an isolated bubble, it interacts with its galactic environment. Passing stars can not only send comets hurtling toward us but can also strip comets away from our Sun's grasp, sending them adrift among the stars. It's possible that our Sun's Oort Cloud has even captured objects that originated from other star systems, blurring the line between what belongs to our Sun and what belongs to the galaxy. Fact 6. The ghostly nature of the cloud. Despite containing trillions of objects, the Oort Cloud is incredibly sparse. The comets within it are separated by immense distances, typically tens of millions of kilometers from one another. If you were to travel through the Oort Cloud in a spacecraft, you would be extremely unlikely to see anything at all. The sky would appear as an empty, black void, with the Sun looking like just another very bright star. The term cloud is misleading. It's more like a cosmic mist, an almost imperceptible haze of icy bodies spread across an immense volume of space. It's a silent, dark, and profoundly lonely space, where each icy rock drifts in almost perfect isolation for eons. Fact 7. Pristine remnants of creation. The objects in the Oort cloud are considered to be some of the most primitive and unaltered materials in our entire solar system. Because they were thrown into the deep freeze of outer space so early in the solar system's history, they have remained largely unchanged for over 4 billion years. Unlike planets and asteroids closer to the Sun, they haven't been subjected to significant heating, geological processing, or collisions. This makes them invaluable scientific targets. By studying the composition of comets that originate from the Oort cloud, scientists can look back in time, analyzing the original chemical and physical conditions of the nebula from which our Sun and planets were born. Fact 8. The power of indirect evidence. No one has ever seen the Oort cloud directly, and it's unlikely we ever will with current technology. Its existence is inferred entirely from indirect evidence, a beautiful example of scientific deduction. Jan Oort and other astronomers noticed that long-period comets seem to arrive from all directions in the sky with equal probability, not from the flat plane where the planets reside. This suggested they originated from a vast, spherical shell surrounding the solar system. Furthermore, by analyzing their orbits, they calculated that these comets were coming from incredibly far away. The theory of the Oort cloud is the most elegant explanation that fits these observations, a testament to how we can understand the universe's grandest structures by observing the small messengers they send our way. Fact 9. The galactic tides. Gentle-handed isn't just passing stars that can disturb the Oort cloud. A constant, gentle force from our entire Milky Way galaxy also plays a crucial role. This is the galactic tide. Just as the moon's gravity creates tides in Earth's oceans, the combined gravity of the galaxy's disk of stars, gas, and dark matter exerts a tidal force on our solar system. For objects as loosely bound as those in the Oort cloud, this subtle stretching and squeezing force is significant. Over millions of years, the galactic tide can slowly alter the orbits of comets, raising one end of their orbit and lowering the other. This process is a primary driver for sending a steady trickle of long-period comets from the cloud into the inner solar system. Fact 10. A star passed through about 70,000 years ago, when early humans were sharing the planet with Neanderthals. A small red dwarf star known as Scholz's star and its brown dwarf companion passed through the outer regions of our Oort cloud. This is the closest known stellar flyby in our solar system's history. While it didn't cause a major disruption at the time, this event would have sent gravitational ripples through the cloud. Astronomers believe that this passage likely perturbed the orbits of many comets. Some of these comets may have been nudged onto new paths that will bring them into the inner solar system, but due to the immense distances, they won't arrive for another 2 million years. It's a quiet reminder that our solar system is not isolated, but part of a dynamic, moving galaxy. Fact 11. The immense mass of the cloud. While the Oort cloud is incredibly sparse, the sheer number of objects within it adds up to a significant amount of mass. Current estimates, though wide-ranging, suggest that the total mass of the Oort cloud could be several times that of Earth. Some models even propose it could be as massive as 10 to 100 Earth masses, which would make it more massive than the entire asteroid belt and Kuiper belt combined. This mass is not concentrated but is spread out over a volume of space trillions of times larger than the space occupied by the planets. It is a quiet testament to the inefficiency of planet formation. A huge amount of the solar system's original building blocks were not incorporated into planets but were instead exiled to this distant reservoir, where they remain in a state of suspended animation, a hidden repository of our system's primordial matter. Fact 12. The composition of an Oort cloud comet. What exactly are these icy bodies made of? An Oort cloud object, often called a cometary nucleus, is essentially a cosmic snowball or a dirty snowball, as famously described by astronomer Fred Whipple. The primary ingredient is water ice, frozen solid for billions of years. Mixed in with this water ice are other frozen gases, such as carbon monoxide, carbon dioxide, methane, and ammonia. These are substances that would be gases here on Earth but are frozen solid in the extreme cold of the outer solar system. Finally, interspersed throughout this icy mixture is a significant amount of dust and rock, composed of silicates and carbon-rich organic compounds. These organic molecules are not life itself but are the fundamental building blocks from which life can arise, making comets a subject of intense interest in the study of astrobiology. Fact 13. A realm of absolute stillness. The Oort Cloud is a place of almost perfect stillness and silence. Sound, as we know it, requires a medium through which to travel, like air or water. In the near-perfect vacuum of the Oort Cloud, there is no medium. The silence is absolute and eternal. There is no wind, no atmosphere, and no sound waves to disturb the profound quiet. The comets themselves drift without a whisper. Even if two were to collide, an extraordinarily rare event given the vast distances between them, the impact would be a silent flash of light and debris, dissipating into the void without an audible trace. This deep, unbroken silence is one of the defining features of this distant realm, a place where the only motion is the slow, silent pull of gravity over millions of years. Fact 14. The colors of the comets. While we often imagine comets as brilliant white objects, the nuclei of Oort Cloud comets are actually some of the darkest, least reflective objects in the solar system. Their surfaces are not pristine white ice. Over billions of years, exposure to cosmic rays and ultraviolet radiation from distant stars has triggered chemical reactions on their surfaces. This process, known as space weathering, creates a dark, crusty layer of complex carbon-based organic molecules, similar to tar or asphalt. This dark crust can cover a much icier interior. When a comet is nudged toward the sun, heat penetrates this crust, causing the ices beneath to vaporize and burst through, creating the bright coma and tail that we see. The nucleus itself, however, remains a dark, enigmatic object, hiding its bright, icy heart beneath a dark, ancient mantle. Fact 15. The strange case of Sedna. While not technically an Oort Cloud object, the dwarf planet Sedna provides tantalizing clues about the cloud's inner structure. Sedna has one of the most unusual orbits ever discovered. It is incredibly elongated, taking it from just beyond the Kuiper belt to a distance nearly 1,000 times that of Earth from the Sun. Critically, its closest approach to the Sun is still too far away to be significantly influenced by Neptune's gravity. This has led astronomers to classify it as a detached object, or a potential member of the inner Oort Cloud, the Hills Cloud. Its existence suggests that something powerful, perhaps a passing star long ago, or even an undiscovered ninth planet, pulled it into this strange, isolated orbit. Sedna is a mysterious outlier, a lone wanderer whose path hints at the unseen structure and history of this distant region. Fact 16. The temperature of deep space. The Oort Cloud is unimaginably cold. Far from the warming influence of the Sun, the temperature of an object in this region hovers at just a few degrees above absolute zero. At these temperatures, around -265 to 270 degrees Celsius, -445 to 454 degrees Fahrenheit, molecular motion almost ceases. The water ice is harder than granite, and gases like nitrogen and carbon monoxide are frozen solid. This extreme cold is precisely why the comets there are so well preserved. There is northwest heat to drive chemical reactions or alter their composition. They are locked in a state of perfect cryogenic preservation, holding their secrets for billions of years. This deep freeze ensures that when one of them finally journeys toward the Sun, it offers us a chemically pure sample of the early solar system. Fact 17. No direct observations. It is important to remember that every fact we know about the Oort Cloud is an inference. We have never taken a picture of it. We have never sent a probe through it. The individual comets are far too small, dark, and distant to be seen with any current or foreseeable telescope. They are like single grains of sand scattered across a continent. We only know they are there because of the long-period comets they send our way. It is a structure so grand in scale that it is invisible, its presence revealed only by the gravitational echoes and the celestial messengers it occasionally dispatches from the darkness. Studying the Oort Cloud is an exercise in cosmic archaeology, piecing together the story of a vast, unseen empire from the few artifacts that happen to wash ashore. Fact 18. How Jan Oort conceived it. The story of the Oort Cloud's discovery is a masterpiece of logical reasoning. In 1950, Dutch astronomer Jan Oort was studying the orbits of long-period comets. he noticed two key things. First, none of them seemed to have orbits that suggested they came from interstellar space, they were all bound to the Sun. Second, he observed a statistical anomaly. Many comets had their farthest point, aphelion, at a similar, vast distance of around 20,000 astronomical units. He reasoned that something must be disturbing comets at this distance, sending them on their first ever trip toward the Sun. He proposed a vast reservoir, or cloud, of comets that had existed since the solar system's formation, and that passing stars would occasionally rattle this cloud, sending a few of its members our way. His theory has remained the cornerstone of our understanding ever since. Fact 19. The definition of the solar system's edge. Where does our solar system truly end? The Oort cloud provides the best answer. It is not defined by the last planet or the termination shock of the solar wind. The true boundary of the solar system is the edge of the Sun's gravitational dominance, the point where its gravitational pull is no longer the primary influence on an object. This is called the Hill sphere, and the Oort cloud extends to nearly its full radius. Beyond this boundary, the gravity of the Milky Way galaxy takes over. The Oort cloud, therefore, occupies the very frontier of our solar system. Its outermost comets are perched precariously on this gravitational edge, able to be pulled inward toward the Sun or cast away into the interstellar void by the slightest external nudge. Fact 20. The threat of a stellar encounter. While the passage of Scholz's star 70,000 years ago was relatively benign, a closer, or more massive stellar encounter could have dramatic consequences. If a large star were to pass directly through the Oort cloud, it could trigger a comet shower, sending a vastly increased number of comets hurtling into the inner solar system. Such an event would dramatically increase the frequency of cometary impacts on planets, including Earth. Geological records on Earth show evidence of periodic mass extinctions, and while asteroid impacts are a known cause, some scientists have theorized that a comet shower, triggered by a stellar passage or the solar system's movement through the galactic plane, could be responsible for some of these cyclical extinction events. The quiet Oort cloud, therefore, holds a potential, albeit remote, threat to life on Earth. Fact 21. The spherical shape and its importance. The Oort cloud is not a flat disk like the asteroid belt or the Kuiper belt. It is a sphere that completely surrounds the Sun and the planets. This spherical shape is a crucial piece of evidence for its origin story. If the cloud had formed in place, it would likely be flat, following the same orbital plane as the rest of the solar system. The fact that it is spherical tells us that its objects were scattered from the planetary region in all directions. The gravitational kicks from the giant planets were random, flinging the icy bodies into orbits with every possible inclination and orientation. Over billions of years, these chaotic, random orbits averaged out into the vast, spherical distribution we infer today. This shape is a fossilized record of the solar system's chaotic and violent youth. Fact 22. New comets from the cloud. When a comet makes its very first journey from the Oort cloud into the inner solar system, it is referred to as a new comet. These first-time visitors are often unusually bright and active. This is because their surfaces are coated with highly volatile materials, such as frozen nitrogen, methane, and carbon monoxide, which have never before been exposed to significant sunlight. As they approach the Sun, these supervolatile ices vaporize at very large distances, producing a huge, spectacular cloud of gas and dust. However, this initial burst of activity is short-lived. After this first pass, the most volatile ices are largely depleted, and on any subsequent returns, thousands or millions of years later, the comet will be significantly fainter. Observing a new comet is like witnessing the awakening of an ancient object that has slept in the dark for eons. Fact 23. The fading of a comet. Not all comets that fall from the Oort cloud survive their journey. Each pass around the Sun takes a heavy toll on a comet. With every approach, it loses a significant portion of its mass as its ices are vaporized by the Sun's heat, carrying dust away in the process. A comet literally evaporates over time. Some comets may break apart completely due to the thermal stress or the Sun's powerful gravitational forces. Others may simply exhaust all their volatile ices after many orbits, eventually becoming dark, inactive, and asteroid-like objects. This process of fading means that the beautiful comets we see are temporary phenomena. They are celestial icebergs slowly melting in the solar fire, and the Oort cloud is the distant, cold ocean from which they originate, a constant source of new icebergs for the Sun to consume. Fact 24. Random orbital inclinations. Unlike the planets, asteroids, and most Kuiper belt objects, which orbit the Sun on or near a flat plane called the ecliptic, objects in the Oort cloud have no preferred orbital plane. Their orbits are inclined at all possible angles. A comet from the Oort cloud is just as likely to enter the inner solar system from the north or south as it is along the same plane as Earth. This randomness is another key piece of evidence that they were gravitationally scattered into their current positions. It also explains why long-period comets appear to come from any and all points in the night sky. They are not confined to the narrow band of the zodiac where we see the planets. This spherical, randomly oriented distribution paints a picture of a truly three-dimensional solar system, far grander than the flat system we are familiar with. Fact 25. The long, slow evolution. The Oort cloud is not a static object, it has been slowly evolving for billions of years. Its total population of comets has likely decreased over time. The same gravitational perturbations from passing stars and the galactic tide that send comets inward can also strip them away from the solar system entirely, casting them into interstellar space. The cloud is slowly evaporating into the galaxy. The rate of this loss is very slow, but over the entire 4.5 billion-year history of the solar system, it is thought that a significant fraction of the original cloud has been lost. The Oort cloud we see today is a remnant, a smaller, more tightly bound version of the even grander cloud that may have existed in the distant past. It is a dynamic structure, constantly shaped by its galactic environment. Fact 26. A net for interstellar visitors. Just as the Oort cloud can lose comets to interstellar space, it is also theoretically possible for it to capture objects from other star systems. If another star with its own cometary cloud passes close enough, there can be an exchange of material. The Sun's gravity could potentially snag a comet from the visiting star's cloud, incorporating it into our own Oort cloud. While the probability of this is low, over billions of years, it is not impossible. This raises the fascinating possibility that our Oort cloud may not be composed entirely of native solar system material. It could be a hybrid collection, containing a few rare immigrants from distant, unknown star systems, each one a captured alien artifact holding clues about the chemistry of another world's birthplace. Fact 27. Probing the cloud with Voyager. The Voyager 1 and 2 spacecraft, launched in 1977, are currently traveling through the region between the Sun's heliosphere and interstellar space. They are the most distant human-made objects, but even they're nowhere near the Oort cloud. At its current speed, it will take Voyager 1 about 300 years just to reach the inner edge of the Oort cloud, and an astonishing 30,000 years to pass through its entirety. Even then, the chances of it passing close enough to an Oort cloud object to see it are practically zero, given the immense emptiness of the region. The Voyager probes serve to highlight the almost incomprehensible scale of the Oort cloud. They are the fastest objects we have ever dispatched, yet the cloud's frontier remains a journey of millennia for them. Fact 28. Nemesis, the Sun's hypothetical companion. In the 1980s, a controversial hypothesis proposed that the Sun might have a dim, undiscovered companion star, a red dwarf or brown dwarf, in a very long and eccentric orbit. This hypothetical star was named Nemesis. The theory suggested that every 26 million years, Nemesis would pass through the Oort cloud, triggering an intense comet shower that would cause the cyclical mass extinctions seen in Earth's fossil record. While this is a captivating idea, there is very little direct evidence to support it. Extensive sky surveys have not found a star with the predicted characteristics. Although the Nemesis hypothesis is not widely accepted today, it remains a powerful thought experiment about how the quiet Oort cloud could be linked to the dramatic history of life on our own planet. Fact 29. Different chemistry from inner comets. By analyzing the light from comets, scientists can determine their chemical composition. They have found subtle but important differences between comets from the Oort cloud and those from the closer Kuiper belt, like Halley's comet. Oort Cloud comets tend to be richer in certain long-chain carbon molecules and have different isotopic ratios for some elements. This is believed to reflect the different formation environments of their parent bodies. Oort Cloud comets formed in the warmer, denser region among the giant planets, while Kuiper belt objects formed farther out in a colder, less dense environment. These chemical fingerprints allow astronomers to trace a comet's origin, determining whether it is a visitor from the nearby Kuiper belt or a true messenger from the deep freeze of the Oort Cloud. Fact 30. The ultimate fate of the cloud. The Oort Cloud will not last forever. Like the Sun itself, it has a finite lifespan. Over the next few billion years, it will continue to lose comets to interstellar space through galactic tides and stellar encounters. Eventually, when the Sun reaches the end of its life, its fate will be sealed. In about 5 billion years, the Sun will expand into a red giant, its outer layers engulfing the inner planets. While this will not directly affect the distant Oort Cloud, the Sun will lose a significant amount of its mass in the process. This reduction in mass will weaken its gravitational hold on the Oort Cloud comets. Many will drift away, released from their ancient orbits to wander the galaxy as interstellar orphans. The vast, silent shell that guarded our solar system for its entire life will finally dissipate into the void. Fact 31. The influence of giant molecular clouds. Passing stars are not the only massive objects that can gravitationally disturb the Oort Cloud. On its long journey around the galactic center, our solar system occasionally passes through or near giant molecular clouds. These are immense interstellar clouds of gas and dust, the stellar nurseries where new stars and planets are born. They can be hundreds of light years across and contain millions of times the mass of our Sun. A close passage to one of these clouds would exert a powerful gravitational tidal force on the Oort Cloud, far stronger than that of a single passing star. Such an encounter could dislodge a vast number of comets, potentially triggering one of the most intense comet showers the inner solar system has ever experienced. These colossal, dark clouds are a slow but powerful agent of change for our solar system's distant frontier. Fact 32. The near parabolic orbits. When astronomers plot the paths of new comets arriving from the Oort Cloud, they find that their orbits are not simple ellipses but are almost parabolic. A parabolic orbit is the exact escape trajectory. An object on such a path has just enough energy to escape the Sun's gravity and never return. This is a crucial clue. It tells us that these comets arrive with almost zero velocity relative to the Sun, as if they were sitting perfectly still in the distant cloud before being gently nudged. This observation strongly supports the idea of a distant, stable reservoir. If they were interstellar visitors, they would arrive with much higher speeds on hyperbolic trajectories. The near-parabolic nature of their paths is a clear signature, a whisper from the void that tells us they are native members of our solar system, falling from its most distant edge. Fact 33. A comet's D-type composition. Many comets originating from the Oort Cloud are classified as D-type, which refers to their spectral characteristics. D-type objects are very dark, with a reddish, featureless spectrum in visible light. This coloration is believed to be due to the presence of complex, carbon-rich organic compounds, known as tholins, on their surfaces. These materials are created over billions of years as simple ices like methane and nitrogen are irradiated by cosmic rays. This dark, reddish material is common in the outer solar system, also found on some asteroids and moons of the giant planets. The D-type classification links Oort Cloud comets to other primitive bodies, suggesting a shared origin in the early solar nebula before they were scattered to their current, disparate locations. They are, in essence, frozen relics from the same primordial chemical soup. Fact 34. The Oort Cloud and Planet 9. The intriguing Planet 9 hypothesis, the idea of a large, undiscovered planet orbiting in the far outer solar system, is deeply connected to the Oort Cloud. Some of the most compelling evidence for Planet 9 comes from the strange, clustered orbits of a handful of distant Kuiper belt objects. Proponents of the theory suggest that the gravitational influence of this massive planet is shepherding these objects into their unusual paths. If Planet 9 exists, it would essentially act as a shepherd for the inner edge of the Oort Cloud, the Hills Cloud. Its gravity could be a dominant force in this region, shaping the orbits of objects there and helping to detach them into orbits like Sedna's. The search for Planet 9 is, in part, a search for a missing piece of the puzzle that connects the Kuiper belt to the vast, unseen Oort cloud beyond. Fact 35, the pressure of sunlight. Even in the inner solar system, the pressure exerted by sunlight itself is a gentle but persistent force that can affect cometary debris. While the icy nucleus of a comet is too massive to be moved by sunlight, the tiny dust particles released in its tail are a different story. As a comet from the Oort cloud approaches the sun, it releases a stream of gas and dust. The solar wind pushes the gas, ion, tail directly away from the sun, but the dust particles are gently pushed by the pressure of the photons themselves. This radiation pressure causes the dust tail to lag behind the comet in its orbit, creating its characteristic gentle curve. It is a quiet, beautiful demonstration of the fact that light itself can exert a physical force, a celestial breeze that sculpts the ghostly tails of these visitors from the void. Fact 36, a sphere of trillions. The sheer number of objects in the Oort cloud is staggering. While we may only see a handful of long-period comets in a lifetime, the reservoir they come from is thought to contain trillions, that is, a million, of cometary nuclei larger than 1 kilometer in diameter. If you were to gather all of these objects together, they would form a body several times more massive than Earth, yet they are spread so thinly that the region is mostly empty space. This immense population is a necessary part of the theory. For us to see even a few comets, there must be a vast number available to be perturbed. For every successful comet sent on a journey inward, countless trillions more continue their slow, silent orbits, undisturbed in the dark. Fact 37, the cosmic ray environment. Objects in the Oort cloud are constantly bathed in a sea of high-energy particles known as galactic cosmic rays. These are atomic nuclei that have been accelerated to nearly the speed of light by distant supernovae and other violent cosmic events. Here on Earth, we are largely protected from them by our atmosphere and magnetic field. But in the Oort cloud, there is no such shield. Over billions of years, this constant, gentle rain of radiation penetrates the top few meters of a comet's surface. It breaks down simple molecules like water and methane and helps to form the complex, dark, organic crust characteristic of cometary nuclei. This cosmic ray bombardment is a key process of space weathering, slowly altering the chemistry and appearance of these ancient bodies, giving them their dark and aged exterior. Fact 38, the source of some meteor showers. While most of the famous annual meteor showers, like the Perseids or Leonids, are caused by debris from short-period comets originating in the Kuiper belt, long-period comets from the Oort cloud also leave trails of dust behind them. If Earth's orbit happens to intersect the path of one of these comets, we can experience a meteor shower. However, because these comets have such long and unpredictable orbits, the meteor showers they produce are not annual events. They are often one-time occurrences, or they happen on timescales of thousands of years. Observing a meteor that originated from an Oort cloud comet is a rare and special event, a fleeting connection to a truly ancient and distant traveler that passed through our neighborhood long ago. Fact 39, an unstable, dynamic system. It is a common misconception to think of the Oort cloud as a static, peaceful place. While the timescales are immense, it is a highly dynamic system. The orbits of the comets within it are not stable in the long run. They are constantly being subtly reshaped by the galactic tide and nudged by passing stars. An object's orbit can be changed from nearly circular to highly elliptical, sending it careening toward the sun. Conversely, a comet could be ejected from the solar system entirely. No single comet is guaranteed to remain in the cloud forever. It is a place of constant, slow churning, a celestial waiting room where objects are held for billions of years before one of three fates befalls them: a fiery journey inward, ejection into the galaxy, or simply remaining in their cold, dark orbit until the sun itself dies. Fact 40, the sun's motion through the galaxy. The sun is not stationary, it travels through the Milky Way galaxy, orbiting the galactic center about once every 230 million years. This journey takes it through different galactic environments. Sometimes it passes through denser regions of the galaxy, like the spiral arms, where star density is higher and encounters with other stars or molecular clouds become more likely. At other times, it passes through less dense regions. This galactic environment has a direct impact on the Oort cloud. It is believed that the rate at which comets are sent into the inner solar system is not constant but varies depending on where the Sun is in its long journey. The Oort cloud acts as a sensitive barometer, reacting to the local galactic weather and recording the history of the Sun's passage through the Milky Way. Fact 41. The Oort cloud and the nebular hypothesis. The existence of the Oort cloud is a natural and necessary prediction of the modern nebular hypothesis, the theory of how our solar system formed. This theory states that the Sun and planets condense from a vast, rotating cloud of gas and dust. During the final stages of planet formation, the region of the giant planets was a chaotic place, filled with leftover icy and rocky planetesimals. The nebular hypothesis predicts that the powerful gravity of Jupiter and Saturn would have ejected a massive number of these bodies. The Oort cloud is the logical destination for the ones that were thrown far out but did not quite escape the Sun's gravity. In this way, the Oort cloud isn't just a strange, separate feature, it's the attic of the solar system, the place where all the leftover construction materials were stored, perfectly validating our modern understanding of planetary creation. Fact 42. The deuterium to hydrogen ratio. One of the key chemical clues scientists use to trace the origin of water is the ratio of deuterium, a heavy isotope of hydrogen, to normal hydrogen, known as the D/H ratio. Earth's oceans have a very specific D/H ratio. Scientists have measured this ratio in comets to see if they could have delivered Earth's water. The results are fascinatingly complex. Some Kuiper belt comets have a D/H ratio much higher than Earth's oceans. However, several comets thought to originate from the Oort cloud, like Comet Hartley 2, have a D/H ratio that is a near-perfect match. This suggests that at least some of Earth's water likely came from comets formed in the Jupiter-Saturn region, the very comets that were later exiled to form the Oort cloud. These chemical fingerprints are powerful tools for connecting our living world to the cold, distant realm of comets. Fact 43. A world without light. The Oort cloud is a realm of profound and perpetual darkness. At such an immense distance, the Sun would appear as nothing more than an exceptionally brilliant star, brighter than any other, but too small to be seen as a disk with the naked eye. It would cast no warming rays and provide no meaningful illumination. The ambient light would be the faint, collective glow of the distant Milky Way and other galaxies. An object in the Oort cloud receives thousands of times less sunlight than Pluto does. This is a darkness that is almost absolute, a place where the only light is the cold, ancient starlight from across the galaxy. This eternal night is what preserves the comets in their frozen state, protecting their volatile ices from the solar radiation that would otherwise make them disappear. Fact 44. The possibility of rogue planets. Our galaxy is likely home to billions of rogue planets, planets that were ejected from their own star systems and now wander through interstellar space alone. On rare occasions, over billions of years, it is possible that a rogue planet could pass through our Oort cloud. Such an event would be far more disruptive than the passage of a small star. A Jupiter-sized rogue planet, for instance, would carve a gravitational tunnel through the cloud, flinging comets in all directions. It would likely trigger a massive and long-lasting comet shower in the inner solar system while simultaneously stripping away a large portion of the cloud into interstellar space. While purely theoretical, the possibility serves as a reminder that even the vast and quiet Oort cloud is not immune to the occasional intrusion of large, dark wanderers from other systems. Fact 45. Distinguishing from interstellar objects. With the discovery of interstellar objects like Oumuamua and Borisov passing through our solar system, a new question arose. How do we know a comet is from the Oort cloud and not just another interstellar visitor? The answer lies in the object's trajectory and speed. As mentioned before, Oort cloud comets fall in on near-parabolic orbits, traveling at the exact escape velocity. Interstellar objects, however, arrive with their own momentum from their journey between the stars. They travel much faster, on a distinctly hyperbolic trajectory, swinging past the Sun at a speed too great for its gravity to capture. By precisely measuring an object's path through the sky, astronomers can calculate its velocity and determine whether it is a loosely bound member of our own solar system falling from the darkness, or a true alien from another star. Fact 46. The size distribution of comets. The trillions of objects in the Oort cloud are not all the same size. Like asteroids and other celestial populations, they are thought to follow a size distribution where small objects are vastly more common than large ones. There are likely trillions of kilometer-sized bodies, but perhaps only billions of 10-kilometer-sized bodies, and maybe only thousands of giant comets over 100 kilometers in diameter. The Hale-Bopp comet, which was visible for 18 months in the late 1990s, was an unusually large and active Oort cloud comet, estimated to be about 60 kilometers across. Most of the comets that visit us are probably much smaller. This distribution of sizes reflects the original population of planetesimals from the early solar system, a cosmic rubble pile where small bricks vastly outnumber large boulders. Fact 47. Geologically dead worlds. The cometary nuclei in the Oort cloud are geologically dead. Unlike planets or large moons, they are far too small to have retained any internal heat from their formation. There is no volcanism, no tectonic activity, and northwest liquid water to drive geological processes. Their surfaces are shaped only by two forces: the very slow erosion and chemical changes caused by space weathering, and the occasional, extremely rare impact from another Oort cloud object. For billions of years, they have remained inert and unchanged. They are not worlds in the way we think of planets. They are frozen fragments of history, static and silent, offering a window not into planetary evolution, but into the conditions of the solar system's absolute beginning. Fact 48. The Hills cloud is a stable reservoir. The inner, disc-shaped part of the Oort cloud, known as the Hills cloud, is thought to be much more densely packed and more stable than the outer spherical shell. While the outer cloud is vulnerable to disruption by passing stars and the galactic tide, the Hills cloud is more tightly bound to the Sun and is largely immune to these disturbances. This makes it an ideal long-term reservoir. Scientists believe that the Hills cloud acts as a source that slowly repopulates the outer cloud over billions of years. As comets are stripped from the outer cloud, their numbers are gradually replenished by objects whose orbits are slowly perturbed outward from the inner, more stable disk. This inner cloud ensures the longevity of the Oort cloud as a whole. Fact 49. A buffer against the interstellar medium. The Oort cloud, along with the Sun's heliosphere, acts as a massive buffer zone between the planetary part of our solar system and the raw interstellar medium. The interstellar medium is not a perfect vacuum. It contains wisps of gas, dust, and cosmic rays. The sheer size of the Oort cloud means that our solar system occupies a vast bubble of space that is gravitationally ours. Any interstellar material drifting through must first pass through this immense, sparse sphere of comets. While the effect is minimal, the cloud is our first line of defense and our first point of contact with the galactic environment. It is the porous, almost intangible border that separates our cosmic home from the great wilderness of the galaxy beyond. Fact 50. The philosophical edge of home. Contemplating the Oort cloud offers a unique philosophical perspective. It represents the ultimate boundary of our home. For all of human history, we have looked up at the sun, moon, and planets as our celestial neighborhood. The discovery of the Kuiper belt expanded that neighborhood. But the Oort cloud defines its absolute limit. It is a structure so vast that light takes more than a year to cross it, yet it is entirely bound to our sun. It is a part of our solar system, yet it is a place we can never truly see or visit. Knowing that our sun's influence extends into this immense, dark, and silent sphere of ancient ice can create a profound sense of both scale and isolation, a feeling of being on a small, warm island in an impossibly vast and cold cosmic ocean. Fact 51. The sun's lost sibling stars are not typically born in isolation but in large groups or clusters within giant molecular clouds. This means our sun was likely born with hundreds or thousands of sibling stars. In the early days of the solar system, these sibling stars would have been much closer than stars are to us today. The gravitational influence of these nearby stars would have played a crucial role in shaping the nascent Oort cloud. Their gravity would have helped to perturb the scattered planetesimals into more stable, spherical orbits, effectively stirring the cloud into its final shape. It's a humbling thought that the structure of our solar system's most distant realm was likely co-created with the help of long-lost stars that have since drifted across the galaxy, their connection to our sun now severed by billions of years of cosmic travel. Fact 52. The tumbling of a comet. The cometary nuclei within the Oort cloud do not spin in a stable, orderly fashion like a planet. Having been violently ejected from the inner solar system, and subject to uneven outgassing on any previous solar passes, most would have a complex and chaotic rotation. They are expected to be tumbling through space, rotating slowly and irregularly around multiple axes. This slow, unpredictable tumble would mean that a comet has no permanent day or night side. Over long periods, all parts of its surface would be equally exposed to the faint starlight and cosmic rays of the interstellar medium. This chaotic spin is a silent testament to the violent and haphazard forces that placed these objects in their distant orbits billions of years ago. Fact 53. No contribution to zodiacal light. In a clear, dark night, you can sometimes see a faint, triangular glow in the sky after sunset or before sunrise. This is the zodiacal light, and it's caused by sunlight scattering off a disk of dust particles that fills the inner solar system, mostly originating from asteroid collisions and short-period comets. The Oort cloud, despite its immense population of objects, contributes absolutely nothing to this phenomenon. It is simply too far away, and its dust is far too sparse. The dust particles within the Oort cloud are spread so thinly that they create no discernible glow. The zodiacal light is a feature of the inner, flat plane of the solar system, while the Oort cloud remains a separate, invisible, and truly dark sphere. Fact 54. The Great Migration of Planets. The formation of the Oort cloud is deeply tied to the theory of planetary migration. Models of the early solar system suggest that the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form in their current orbits. They likely formed closer together and then migrated over millions of years. This migration was a period of intense gravitational chaos. As the planets shifted their orbits, their gravitational influence swept through the surrounding disk of icy planetesimals, scattering them with incredible efficiency. This planetary reshuffling, particularly the outward migration of Neptune, is now believed to be the primary mechanism responsible for populating both the Kuiper belt and the Oort cloud. The Oort cloud, therefore, serves as a fossil record of this grand migration, its existence a direct consequence of the giant planet's stately dance. Fact 55. The view from within the cloud. Imagine floating alongside a comet in the outer Oort cloud. What would the sky look like? It would be a scene of profound stillness and beauty. The sky would be permanently black, filled with a breathtakingly clear and dense field of stars, as there is no atmosphere to cause twinkling. The Milky Way would stretch across the void as a brilliant, detailed river of light. The most prominent star in the sky would be our own sun, shining with the brilliance of a welder's torch but appearing as a point of light, not a disk. The familiar constellations would be completely unrecognizable, as our perspective on the nearby stars would be dramatically shifted. It would be a lonely, silent, and deeply peaceful vantage point on the galaxy, from the very edge of our own solar system. Fact 56. The hunt for amino acids. One of the most exciting discoveries in cometary science came from NASA's Stardust mission, which collected samples from a comet's coma. Analysis of these samples revealed the presence of glycine, the simplest amino acid. Amino acids are the essential building blocks of proteins, which are fundamental to life as we know it. Since many comets originate in the Oort cloud, this discovery strongly implies that these life-building molecules are preserved in the deep freeze at the edge of the solar system. It supports the theory of panspermia, the idea that comets and asteroids could have delivered the essential chemical ingredients for life to the early Earth. The quiet, cold Oort cloud may, in fact, be a vast repository of the very molecules that made life on our planet possible. Fact 57. The lack of a magnetic field. Planets like Earth have a global magnetic field generated by the motion of molten metal in their cores. This magnetic field protects us from the solar wind and cosmic rays. A comet nucleus in the Oort cloud, being a small, frozen, and geologically inert body, has no such internal dynamo. It generates no magnetic field of its own. It is completely exposed to its environment. When it journeys toward the sun, it does interact with the sun's magnetic field, which is carried outward by the solar wind, creating a complex but temporary magnetic environment around the comet. But in its native home in the Oort Cloud, a comet is a simple, non-magnetic object, drifting silently through the galaxy's own weak magnetic field. Fact 58. The elusive inner Oort Cloud. While the outer, spherical Oort Cloud is the source of the long-period comets we see, the inner Hills cloud remains almost entirely theoretical and unobserved. Its existence is inferred because a stable inner reservoir is needed to replenish the outer cloud over billions of years. Objects in this inner region, like Sedna, are too far away to be affected by the giant planets, but too close to be significantly perturbed by passing stars. This makes them incredibly stable, and therefore very difficult to dislodge and send our way. This region is one of the last truly unexplored frontiers of our solar system. It may hold a population of objects even more massive and numerous than the outer cloud, a quiet, hidden sea of comets just waiting for a sufficiently strong gravitational tide to reveal its secrets. Fact 59. The great uncertainty of its size. While we speak of the Oort cloud's size and mass, it is crucial to remember that these are estimates with huge uncertainties. We cannot see it, so we must model it based on the handful of comets it sends us. We estimate its outer boundary to be around 50,000 to 100,000 Australian dollars, astronomical units, but it could extend even farther. We estimate its mass to be several times that of Earth, but some models allow for it to be much less, or much more. We estimate it holds trillions of objects, but the exact number is unknown. The Oort cloud is a statistical ghost. Its properties are defined by probabilities and models, not direct observation. It is a beautiful example of how science works at its limits, painting a picture of a colossal structure from the faintest of indirect clues. Fact 60. A comet's first sunburn. A new comet arriving from the Oort cloud is experiencing its first ever sunburn. For 4.5 billion years, its surface has only been exposed to the gentle bath of cosmic rays and distant starlight. As it falls toward the sun, it is suddenly subjected to an overwhelming flood of energy and radiation. The ultraviolet light from the sun is particularly effective at breaking down the chemical bonds of the dark, organic crust that has built up over eons. This intense radiation, combined with the heat that vaporizes the insulating layer of supervolatile ices, is what triggers the spectacular outgassing that makes new comets so bright. It is a violent and rapid awakening, as the ancient, weathered skin of the comet is seared and blasted away, revealing the pristine, primordial ices that have been hidden in darkness since the dawn of the solar system. Fact 61. The NICE model and its predictions. A leading theory of solar system evolution, known as the NICE model, provides a detailed narrative for the Oort cloud's formation. It proposes a scenario where the four giant planets initially formed in a much more compact configuration. A gravitational instability between them, particularly between Jupiter and Saturn, caused their orbits to rapidly shift. This dramatic event, the planetary migration, destabilized the entire primordial disk of planetesimals. According to the NICE model, this single, chaotic event was responsible for scattering the vast majority of these icy bodies. The model predicts that about 99% of the original material was ejected into interstellar space, with only a small fraction being retained to form the distant, stable Oort cloud. The Oort cloud, in this view, is the faint, leftover signature of our solar system's most violent and transformative era. Fact 62. The fluffy nature of comets. Contrary to the image of a solid, hard rock, cometary nuclei are thought to be extremely porous and fragile. They are not dense, solid bodies, but rather fluffy aggregates of ice and dust, held together very loosely by gravity and frozen gases. Their density is often less than that of water, meaning a chunk of a comet would float. This delicate, low-density structure is a relic of their formation process, where tiny ice and dust grains gently clump together in the cold, outer solar nebula. This fragile nature is why comets can break apart so easily when subjected to the thermal and gravitational stresses of a close pass by the sun. They are not cosmic cannonballs, but delicate, cosmic snowballs, whose fluffy structure has been preserved in the deep freeze of the Oort Cloud for billions of years. Fact 63. The Sun's escape velocity. Escape velocity is the speed an object needs to break free from the gravitational pull of a massive body. Close to the Sun, this speed is incredibly high. But in the outer Oort Cloud, the Sun's gravity is profoundly weak. The escape velocity at that distance is minuscule, only a few dozen meters per second. This means that even a tiny gravitational nudge from a passing star can be enough to either slightly slow a comet, causing it to fall inward, or slightly speed it up, pushing it past its escape velocity and sending it adrift into interstellar space. The comets of the Oort Cloud exist in a state of perfect gravitational balance, perpetually teetering on the edge of escape. This delicate equilibrium is the reason the cloud is so sensitive to the subtle gravitational whispers from the rest of the galaxy. Fact 64. The two tails of a comet. When a comet from the Oort Cloud enters the inner solar system, it typically develops two distinct tails, both pointing generally away from the Sun. The first, the ion or gas tail, is composed of vaporized gas that has been ionized, stripped of electrons, by the Sun's ultraviolet radiation. This ionized gas is then pushed directly away from the Sun by the solar wind, a stream of charged particles flowing from the Sun. This tail often glows with a faint blue light. The second tail, the dust tail, is made of solid particles of dust that were mixed in with the ice. These heavier particles are pushed more gently by the pressure of sunlight itself and tend to curve gracefully along the comet's orbital path. Observing these two distinct tails is a beautiful, visual confirmation of the two different forces the Sun exerts on these ancient visitors. Fact 65. A record of the early Sun. The chemical makeup of the Oort Cloud's comets can even provide clues about the nature of our Sun in its infancy. The early Sun was likely more active and had a more powerful solar wind than it does today. This intense early radiation would have affected the chemistry of the protoplanetary disk where the comets formed. By studying the isotopic ratios and molecular abundances in the comets that visit us today, scientists can work backward to understand the environment in which they were born. For instance, the presence of certain heat-altered minerals found in comet dust suggests that material from close to the hot, young Sun was mixed into the outer, colder regions where comets formed. The Oort Cloud is thus not just a record of planetary formation, but also a distant, frozen archive of our own star's fiery youth. Fact 66. The concept of extinct comets. What happens to an Oort Cloud comet after it has made many passes by the Sun? Eventually, it is expected to exhaust all of its volatile ices. When this happens, it can no longer produce a coma or tail. It becomes an extinct comet or a dormant comet. All that is left is a dark, inert nucleus of rock and organic compounds, visually indistinguishable from a small asteroid. It is believed that a significant fraction of the near-Earth asteroids are, in fact, the dead husks of comets, both from the Kuiper Belt and the Oort Cloud. These objects are the ghosts of the solar system, silent reminders that even the most spectacular celestial displays are finite, and that every bright comet is on a long, slow journey toward becoming a dark and silent rock. Fact 67. The great time delay. The Oort Cloud operates on timescales that are almost beyond human comprehension. A gravitational disturbance from a passing star that happens today will not result in a comet arriving in our skies tomorrow, or next year, or even in the next 1,000 years. Given the immense size of the orbits and the slow speeds of the comets, the journey inward from the Oort Cloud takes millions of years. This means that the long-period comets we see today are the result of gravitational nudges that occurred in the distant past, when early hominids roamed the Earth. Conversely, any comets being dislodged by stellar passages happening right now will not reach the inner solar system until a far future epoch, long after everyone currently alive is gone. The cloud has a profound temporal inertia. Fact 68. The power of spectroscopy. Since we cannot visit an Oort Cloud comet and take a sample, except for the rare dust particles collected by missions, our primary tool for understanding their composition is spectroscopy. When a comet's coma is lit by the Sun, the gas molecules within it absorb and re-emit light at very specific wavelengths, creating a unique chemical fingerprint. By capturing the comet's light with a telescope and passing it through a spectrograph, astronomers can separate the light into its constituent colors and read these fingerprints. This allows them to identify the presence of water, carbon monoxide, ammonia, and even complex organic molecules from hundreds of millions of kilometers away. Spectroscopy is our remote sense of taste and smell, allowing us to analyze the primordial ingredients of these cosmic icebergs from afar. Fact 69. Clearing the neighborhood. The modern definition of a planet, established in 2006, requires a celestial body to have cleared its neighborhood of other objects. The existence of the Oort cloud is a perfect illustration of what this means. The giant planets, particularly Jupiter, are gravitationally dominant in their zones. Their formation process involved flinging away trillions of icy bodies, which now populate the Oort cloud. They have profoundly cleared their orbital regions. In contrast, a dwarf planet like Pluto exists within the Kuiper belt, a region crowded with other icy bodies it has not cleared away. The Oort cloud is, in essence, the ultimate collection of all the debris that the major planets so effectively swept out of their own neighborhoods. It is the solar system's cleared rubble, now stored at a safe and stable distance. Fact 70. From chaos to serenity. There is a beautiful duality in the story of the Oort cloud. Its creation was an act of unimaginable chaos and violence. The early solar system was a cosmic shooting gallery, with giant planets gravitationally wrestling and flinging trillions of smaller bodies across vast distances. It was a period of instability and disruption on a system-wide scale. Yet, the result of this chaos was the creation of a realm of profound peace and serenity. The comets that survived were placed in vast, slow orbits where almost nothing ever happens. The Oort cloud today is a place of stillness and stability, where objects drift in quiet isolation for billions of years. It is a perfect example of how, in the cosmos, a period of immense violence can give birth to an eon of perfect tranquility. Fact 71. The origin of centaurs. Centaurs are a class of icy bodies whose orbits are unstable, crossing the paths of the giant planets between Jupiter and Neptune. They are considered to be transient objects, with dynamic lifetimes of only a few million years before they are either ejected from the solar system or perturbed inward to become short-period comets. While many centaurs are thought to originate from the closer Kuiper belt, it's believed that the Oort cloud is also a source. A comet falling from the Oort cloud on a journey toward the Sun can have its orbit gravitationally altered by a close encounter with one of the giant planets. This encounter can trap the comet in the planetary region, changing its vast, long-period orbit into a much shorter, chaotic centaur-like orbit. These objects are essentially refugees from the Oort cloud, temporarily caught in the gravitational web of the giant planets. Fact 72. A homogeneous mixture. Unlike planets, which undergo a process called differentiation where heavier elements sink to the core and lighter materials form a crust, cometary nuclei are thought to be undifferentiated. They are a homogeneous mixture of ice and dust, relatively uniform throughout their interior. This is because they are far too small to have generated the internal heat needed to melt and separate their constituent materials. Their pristine, unlayered structure is a direct window into the conditions of the primordial solar nebula. They are not processed worlds but are instead well-mixed samples of the original ingredients that were present when the solar system was just a swirling cloud of gas, dust, and ice. Every part of a comet, from its surface to its core, tells the same story of its ancient, cold origin. Fact 73. The importance of the frost line. The composition of Oort cloud objects is a direct result of their formation beyond the early solar system's frost line. The frost line was a crucial boundary in the protoplanetary disk, located roughly where the asteroid belt is today. Inside this line, it was too warm for volatile compounds like water, ammonia, and methane to condense into solid ice. Outside the frost line, it was cold enough for these ices to form. This is why the inner planets are rocky and the outer planets are gas and ice giants. The comets of the Oort cloud are made almost entirely of material that formed beyond this line, rich in the very ices that were unavailable in the inner solar system. They are, in essence, ambassadors from the cold side of that ancient dividing line. Fact 74. A comet shower's duration. If a passing star were to disturb the Oort cloud and trigger a comet shower, it would not be a brief, sudden event. The effects would unfold over an immense period of time. Due to the slightly different orbital paths and positions of the perturbed comets, they would not all arrive in the inner solar system at once. Instead, there would be a significant increase in the frequency of long-period comets lasting for several million years. The shower would be more like a long, cosmic drizzle, with an elevated rate of cometary visitors for a period longer than the entire existence of the human species. The Oort cloud's response to a disturbance is as slow and stately as everything else about it, a gradual wave of arrivals rather than a sudden flood. Fact 75, radio astronomy and comets. While optical telescopes see the sunlight reflecting off a comet's dust, radio telescopes provide a different and powerful view. They can detect the faint radio emissions from specific molecules in a comet's coma. As the sun's radiation breaks down simple molecules like water, it creates other molecules like hydroxyl, OH. These molecules emit radio waves at very specific, predictable frequencies. By tuning radio telescopes to these frequencies, astronomers can directly measure the amount of water vaporizing from a comet, essentially tracking its breathing as it nears the sun. This technique has been crucial for analyzing the composition of Oort cloud comets and confirming that their primary component is indeed water ice, just as the dirty snowball model predicts. Fact 76, no impact on Earth's tides or seasons. The Oort cloud, despite its potentially large total mass, has absolutely no discernible effect on our daily lives on Earth. Its gravity is far too diffuse and distant to affect Earth's orbit, cause tides, or influence our seasons. The gravitational pull of our own moon, though much smaller, is hundreds of trillions of times stronger on Earth than the pull of the entire Oort cloud combined. The cloud is a passive and disconnected feature of our solar system in this regard. Its only potential influence on Earth is the very rare, long-term hazard of a cometary impact. Otherwise, it remains a silent, invisible, and gravitationally insignificant presence from our perspective here on the Earth's surface. Fact 77, the search for planetary-sized bodies. Could the Oort cloud hide something much larger than a comet? Some theories speculate that it's possible. During the chaotic scattering phase of the early solar system, it's conceivable that a small, Mars-sized or even Earth-sized planet could have been ejected into a distant Oort cloud orbit. Detecting such a body would be nearly impossible with current technology, as it would be incredibly cold, dark, and distant. However, its gravitational influence could subtly shape a region of the inner cloud. The hypothetical planet 9 is one such candidate for a large body at the inner edge of this region. While the existence of a true planet in the Oort cloud is highly speculative, it remains a tantalizing possibility that our solar system's most distant realm may hold surprises far grander than we currently imagine. Fact 78, the probability of impact. The odds of a long-period comet from the Oort cloud directly striking Earth are incredibly small, but not zero. The inner solar system is a vast and mostly empty place, and Earth is a tiny target within it. For every comet that is sent on a path that brings it inside the orbit of Jupiter, only a tiny fraction will come anywhere near Earth. It is estimated that a large, civilization-altering impact from an Oort cloud comet might occur on average once every few hundred million years. While this is an immense timescale, it is not infinite. It implies that over the long history of our planet, such impacts have likely happened. The Oort cloud is a source of rare but potentially catastrophic events, a cosmic lottery where the chances of winning are low, but the consequences are immense. Fact 79, the end of the comet's journey. For a comet from the Oort cloud, the journey to the inner solar system is a one-way trip toward eventual destruction. Even if it is not completely vaporized or broken apart by the sun, its orbit will be fundamentally changed. The gravitational pull of the giant planets, particularly Jupiter, will almost certainly alter its path. Its vast, million-year orbit will be transformed into a much shorter one, lasting only hundreds or thousands of years. It will become a short-period comet, trapped in the inner solar system until it eventually fades into an extinct, asteroid-like object. A comet never truly returns to the Oort cloud once it has made its first pass. The fall from the distant, quiet realm is permanent, a final descent from a place of ancient stillness into the dynamic and destructive heart of the solar system. Fact 80. The final piece of the puzzle. The Oort cloud represents the final piece in the physical puzzle of our solar system structure. If you imagine the solar system as a series of nested regions, you start with the Sun. Then come the rocky terrestrial planets. Beyond them lies the asteroid belt. Then come the gas and ice giants. Farther still is the disc-shaped Kuiper belt, home to dwarf planets like Pluto. And enveloping all of this, stretching to the absolute limits of the Sun's gravity, is the vast, spherical Oort cloud. It completes the picture, showing that our solar system is not a flat disk that simply ends, but a grand, three-dimensional structure with a colossal, icy sphere defining its true boundary. It is the final, largest, and most mysterious component of our cosmic home. Fact 81. As old as the Sun itself, the Oort cloud is not a recent addition to the solar system. It is an ancient, primordial structure, formed at the same time as the Sun and planets around 4.6 billion years ago. It is a direct relic of the solar system's birth. The icy bodies that populate it were formed in the planetary region and were scattered outward within the first few 100 million years of the solar system's existence. This means the Oort cloud has enveloped our solar system for almost its entire history. The comets drifting within it are some of the oldest, least changed objects we can study. They are not just old rocks, they are pristine samples of the original building materials of our world, preserved in a cosmic deep freeze since the very beginning. When we study a comet from the Oort cloud, we are truly looking back in time to the dawn of our own system. Fact 82. An unpredictable source. Because the process that sends comets inward is random, we can never predict the arrival of a new, long-period comet from the Oort cloud. The gravitational nudges from passing stars or the galactic tide are chaotic and unpredictable over long time scales. Unlike short-period comets like Halley's, whose orbits are well known and whose returns can be calculated to the day, new Oort cloud comets appear in our skies with no advance warning. They are usually discovered by automated sky surveys only a year or two before they reach their closest approach to the Sun. Each new discovery is a genuine surprise, a sudden messenger arriving from a realm so distant and so vast that we have no way of knowing it was on its way until it is almost upon us. Fact 83. The sublimation of different ices. A comet from the Oort cloud is a mixture of many different types of ice, and each one vaporizes, or sublimates, at a different temperature. This creates a fascinating, sequential process as the comet approaches the Sun. Far out, beyond the orbit of Saturn, the intense cold keeps most ices stable. As it gets closer, the most volatile ices, like frozen nitrogen and carbon monoxide, begin to sublimate first, giving the comet its initial burst of activity. Closer still, methane and ammonia will start to vaporize. It is only when the comet gets near the orbit of Mars that the most abundant ice, water, begins to sublimate in large quantities, driving the most spectacular activity we see. This sequence of vaporization at different snow lines allows scientists to probe the different layers of a comet's composition as it makes its long journey inward. Fact 84. A stepping stone to the stars. In the far future, should humanity ever develop the technology for interstellar travel, the Oort cloud could serve as a crucial, albeit challenging, stepping stone. It is the solar system's final frontier. While its objects are incredibly sparse, they are vast reservoirs of water ice and other volatile compounds. Water ice can be broken down into hydrogen and oxygen, providing both breathable air and the most powerful chemical rocket fuel known. A sufficiently advanced spacecraft could potentially hop between Oort cloud objects, mining them for resources to refuel for the next leg of a journey to another star. In this distant future vision, the Oort cloud is transformed from a mysterious, invisible shell into the final outpost of humanity, the last harbor before embarking on the truly immense voyage across the interstellar ocean. Fact 85. The sheer invisibility. It is difficult to overstate how completely invisible the Oort cloud is. If you could magically teleport to a random point within the outer Oort cloud, your view would be one of almost perfect blackness. The nearest comet nucleus, likely a kilometer-sized object, would probably be tens of millions of kilometers away, the distance from Earth to Venus. At that range, a dark, non-reflective body would be utterly undetectable to the human eye. You would feel a profound sense of isolation, floating in an empty void, surrounded by unseen neighbors that are more distant from you than the moon is from the Earth. The cloud is a cloud only in the sense of a statistical grouping over an immense area. From any point within it, it is the definition of empty space. Fact 86. The extremes of an orbit. A comet's journey from the Oort cloud is a tale of two extremes. At its farthest point from the Sun, aphelion, a comet drifts at an incredibly slow speed, perhaps only a few hundred meters per second. For millions of years, it crawls along its path in the cold and dark. But as it falls toward the Sun, gravity accelerates it relentlessly. By the time it whips around the Sun at its closest point, perihelion, it can be traveling at speeds of over 50 kilometers per second, faster than any of our planets. It goes from a cosmic crawl to a blistering sprint. This incredible change in velocity is a direct consequence of its highly elliptical orbit, a quiet reminder of the immense power of the Sun's gravity to command and accelerate these distant visitors from the moment they begin their long fall. Fact 87. A universal architecture. The processes that created our Oort cloud, planet formation and the gravitational scattering of leftover debris, are not unique to our Sun. They are a standard feature of how star and planet systems form. This means that astronomers are confident that most, if not all, stars like our Sun have their own Oort clouds. The space between stars is likely filled with these vast, overlapping spheres of icy bodies. While they are too faint to see, their presence is a fundamental part of galactic architecture. This implies that comets are not a special feature of our solar system, but are among the most common objects in the universe, silent sentinels orbiting countless other stars, each cloud a testament to a history of planetary birth that is repeated across the cosmos. Fact 88. The subtle hues of comet dust. While we might think of dust as being gray or brown, the dust released from Oort cloud comets can have subtle and informative colors. By using special filters on telescopes, astronomers can measure the color of the dust in a comet's coma and tail. Often, this dust has a slightly reddish hue, which points to a composition rich in complex organic molecules, the same tholins that give many outer solar system objects their dark, ruddy appearance. The exact color and reflectivity of the dust can provide clues about the size of the dust grains and their chemical makeup. These subtle color variations are another tool astronomers use to compare different comets and to piece together the story of their common origin in the ancient, dusty, and ice-rich disk that formed our solar system. Fact 89. A single, unifying origin. One of the most elegant aspects of the Oort cloud theory is how it provides a single, unifying origin for a wide variety of solar system objects. It explains the existence of the spectacular long-period comets. It provides a source for the transient centaur population that orbits among the giant planets. It helps to explain the origins of some of the near-Earth asteroids, which are likely the extinct nuclei of once active comets. It even provides a logical destination for the trillions of icy bodies that are a necessary byproduct of planet formation. The Oort cloud is not an ad hoc explanation for one type of object. It is a critical piece of a larger puzzle, a theoretical framework that elegantly connects the chaotic birth of the planets to the celestial visitors we see in our skies today. Fact 90. The challenge of the inner cloud. While we have a good understanding of how the outer Oort cloud is disturbed by external forces, the dynamics of the inner Hills cloud are much more mysterious. This denser, disk-shaped region is too close to the Sun to be significantly affected by passing stars or the galactic tide. So what force is able to nudge objects from this stable reservoir into the outer cloud or send them directly inward? This is an active area of research. The gravitational influence of a hypothetical planet 9 is one leading candidate. Another possibility is that very rare, very close, and slow-moving stellar encounters are responsible. Understanding the mechanism that stirs the inner Oort cloud is a key unsolved problem in understanding the long-term evolution of our solar system's most distant objects. Fact 91. The conservation of angular momentum. The journey of an Oort cloud comet is a perfect demonstration of a fundamental law of physics, the conservation of angular momentum. This principle states that for a rotating or orbiting object, its speed will increase as it gets closer to the center of rotation. You can see this when an ice skater pulls their arms in and spins faster. For a comet in a vast, elliptical orbit, its angular momentum must remain the same. Far out in the Oort cloud, it moves very slowly over a huge distance. As it falls toward the Sun and its orbital distance becomes tiny, its speed must increase dramatically to compensate. The incredible velocity a comet reaches at perihelion is not due to any engine, but is a pure and beautiful consequence of this conserved quantity, a cosmic ice skater pulling in its arms for a dazzlingly fast spin around the Sun. Fact 92. A system in dynamic equilibrium. The Oort cloud is best described as a system in a state of dynamic equilibrium. It is not static, but its overall properties remain relatively stable over long periods. There is a constant, slow loss of comets from the outer cloud as they are stripped away by passing stars or sent on inward journeys. At the same time, there is a constant, slow replenishment of the outer cloud by objects being gradually perturbed outward from the more stable inner Hills cloud. These two processes, loss and replenishment, are thought to be roughly in balance. This equilibrium ensures that the Oort cloud, despite its tenuous nature, has been able to survive for the entire age of the solar system, maintaining its status as a vast, persistent reservoir of comets. Fact 93. The search by occultation. Since we cannot see Oort cloud objects directly, one of the few potential methods for detecting them in their native environment is through stellar occultation. This technique involves monitoring a vast number of distant stars for the faint, brief dimming that would occur if a small, dark object from the Oort cloud were to pass directly in front of one. The chances of any single object lining up perfectly are minuscule, but by using powerful survey telescopes that can monitor billions of stars simultaneously, like the upcoming Vera C. Rubin Observatory, it may be statistically possible to catch a few of these fleeting shadows. Such a detection would be a monumental achievement, providing the first direct confirmation of an object in this distant realm. Fact 94. A source of interplanetary dust. Every time a comet from the Oort cloud passes through the inner solar system, it leaves behind a trail of microscopic dust particles. While the comet itself may leave, this dust remains, slowly spiraling in toward the Sun. Over billions of years, the countless passages of comets have contributed to a faint but pervasive cloud of interplanetary dust that fills the solar system. These tiny particles, often no bigger than grains of smoke, are a constant presence in the space between planets. Occasionally, one will enter Earth's atmosphere as a micrometeorite. The Oort cloud is therefore a slow but steady source for this cosmic dust, a reminder that even after these majestic visitors are long gone, they leave behind a ghostly, microscopic trace of their passage. Fact 95. The blurring line between comet and asteroid. The study of objects from the distant solar system is blurring the traditional lines between comet and asteroid. We once defined comets as icy bodies that grow tails, and asteroids as inert rocks. But we have found asteroids in the main belt that sometimes show cometary activity, and we know that comets from the Oort cloud can become extinct and look just like asteroids. Furthermore, some objects, like the centaurs, have characteristics of both. The modern view is that comet and asteroid are not two distinct types of objects, but rather represent the two ends of a continuous spectrum. The Oort cloud is a reservoir of the most ice-rich, primitive end of that spectrum, containing objects that are fundamentally different from the processed rock of the inner solar system. Fact 96. The future of Oort cloud research. The future of Oort cloud research is bright, even if we can never see the cloud itself. The next generation of sky survey telescopes, particularly the Vera C. Rubin Observatory, will revolutionize the field. This observatory will scan the entire visible sky every few nights with unprecedented depth and precision. It is expected to discover thousands of new comets and other distant objects, including many new visitors from the Oort cloud. This massive increase in data will allow for a much more detailed statistical analysis of their orbits, helping scientists to refine their models of the cloud's size, shape, mass, and population. We will have a much clearer picture of this invisible structure, all by studying the messengers it sends us in far greater numbers than ever before. Fact 97. No weather, no atmosphere. An object in the Oort cloud exists in a state of perfect environmental simplicity. It is too small and too cold to hold any kind of atmosphere. There is no gas, and therefore no wind, no clouds, and no weather of any kind. The concept of a surface is also different from that of a planet. There is no air pressure, only the hard vacuum of space. The only environmental forces are the constant, gentle rain of cosmic rays, the faint light of distant stars, and the incredibly weak pull of the sun's gravity. It is a world stripped down to its most basic elements: ice, rock, and the void. This utter simplicity is what makes these objects such perfect time capsules, as there are no complex geological or atmospheric processes to alter their ancient state. Fact 98. A cosmic shooting gallery over the 4.5 billion year history of the Earth. It is estimated that many thousands of long-period comets from the Oort Cloud have graced the skies of the inner solar system. While only a tiny fraction of these would have resulted in impacts, the inner solar system has been a cosmic shooting gallery, with our planet in the middle. The craters on the Moon stand as a silent record of this long history of bombardment. While asteroids from the main belt are responsible for the majority of impacts, the Oort Cloud has been a consistent, secondary source of large, high-velocity projectiles. The cloud's existence is a quiet reminder that the solar system is not a perfectly safe and orderly clockwork, but a place where rare, violent events are a natural and recurring part of its long-term evolution. Fact 99. A final destination and a beginning. The Oort Cloud represents a place of endings and beginnings. For the icy planetesimals that formed in the chaotic disk of the young solar system, it was a final destination, a place of exile where their development was frozen in time. They ended their chaotic journeys and began a long, quiet existence in the dark. But for any one of these objects that is later perturbed, the cloud becomes a starting point. It is the beginning of a new and final journey, a long fall toward the sun that will result in a spectacular, fleeting display of light and gas, before its ultimate destruction or transformation. The cloud is thus a place of both perfect preservation and latent potential, a realm of endings that holds the seeds of new beginnings. Fact 100. The silent witness. More than any other feature of our solar system, the Oort Cloud is its silent, patient witness. It has been present for everything. It was there when the planets finished forming. It was there when the late heavy bombardment delivered water and organics to the early Earth. It watched as life arose and evolved. It was there, in the deep distance, when dinosaurs roamed the land, and it was there when the asteroid fell that sealed their fate. It has persisted through ice ages and witnessed the rise of humanity. The Oort Cloud is a vast, spherical memory palace, holding the pristine, frozen evidence of the solar system's birth. Its trillions of silent inhabitants are the quiet keepers of our history, circling in the dark, a final, immense, and eternal monument to our cosmic origins.